Okay, we are continuing on chapter 14. We're continuing on chapter 14 here. We were talking about really the common ion effect. And really, the idea of the common ion effect is, again, much like the name implies, you have some type of substance that is going to set up an equilibrium. For example, like a weak acid, like, say, acetic acid. And because, again, it's a weak acid, it will set up that equilibrium and will really just dissociate in the beaker into acetate and some H plus here. And again, if you added a salt or something to it, like sodium acetate with it in that beaker, because sodium acetate is a salt, it will not set up an equilibrium. It will break apart completely into its ions, which are sodium ions and acetate ions. And as we talked about here, the presence of this additional acetate ions in this beaker where we have this equilibrium set up is essentially like Le Chatelier's principle. We are essentially adding more of the acetate in this case, which is a product. And based on Le Chatelier's principle, because we are adding more of it, it will cause the equilibrium to shift there to the left-hand side of the arrow. The result of that is for a weak acid and also a weak base, it will keep basically the weak acid or weak base together. It will not dissociate as much. The result of that in terms of the pH is because it is shifting here to the left in this example, we are shifting away from the H plus there, and we will have a lower H plus concentration in this solution with the common ion than if we had just, say, the acetic acid by itself. And the result of that is we will see the H plus concentration go down. The result of that is we will see the pH really go up in comparison to, say, acetic acid by itself. So I think we did one, it was like 2.7-ish or something like that for the acetic acid. And with the presence of the common ion, like the sodium acetate, we end up with like a pH of 4.9 or something like that. And that is a direct result of this Le Chatelier's principle, where it's kind of forcing the weak acid basically to stay together. The common ion effect is essentially what happens in a buffer, which is the main topic that we talked about at the end there, which is really the same thing as a common ion effect. And a buffer is made up of really a combination of two things, either a weak acid and the salt of its conjugate base, or you can have a buffer that's made up of a weak base and the salt of its conjugate acid. We refer to it as the salt of its conjugate acid because, or the salt of its conjugate base, because it's an ionic compound. It's a salt, and it will have some type of spectator ion typically on it that's not doing much, like a sodium, a potassium, or something of that nature. And it's really important, as we talked about in terms of the function of a buffer, is both of those things has to actually be in the solution to begin with in order for it to actually behave as a buffer. This is also why, as we talked about, you cannot have a buffer that's actually made up of either a strong acid or a strong base. So if you see a strong acid or a strong base, that eliminates the chance of that thing being a buffer. And that's because with a strong acid or strong base, they are not going to stay together. It is a one-way street where they're going to 100% break apart into ions. The result of that is you will not have the two main important things for a buffer, which is a buffer has to have an acid part and it has to have a base part. So in order to have an effective buffer, you have to have both of those things in that solution at the same time. Now, we also talked about how a buffer actually functions, and a buffer actually functions by, because it has an acid part or a base part, ultimately what a buffer is able to do is prevent the formation of free H plus or free OH minus, when you add a strong acid or a strong base to a solution. So if you have a non-buffer and you toss in there some HCl, you're going to add a lot of H plus to that solution really quickly, and that is going to see a pretty big jump downward in the pH. And same thing if you had a non-buffer and you added something like sodium hydroxide to it, that's going to have a lot of hydroxide in that solution freely floating around really quickly. And as we've talked about, the hydroxide and H plus concentration are related to each other. So as the H plus OH minus concentration increases, H plus concentration decreases a lot. And again, you will see a pretty big change in your pH in that case. The difference is when you put that same acid into a buffer, because the buffer has that acid part in there and the base part in the solution to begin with, when you add that HCl, it basically will tie up the H plus that's coming in by the base part of the buffer, and that's going to actually form the other part of the buffer as a result of that. The end result of that is you're not really introducing into that solution a lot of free floating H plus, which is really can affect the pH, and that H plus gets kind of tied up. Same thing when you would add to a buffer here that has, again, the acid part and the base part. When you would add something like sodium hydroxide to it, what's going to happen is when that hydroxide comes in, it's going to react with the acid, and those two guys are going to come together, and it's going to basically make water. And again, essentially what that's going to do is tie up the OH minus in water and not allow it to be freely floating in the solution. Thus, the H plus concentration will remain relatively constant because you haven't introduced a lot of free floating OH minus in that case. By the way, same thing happens. This guy comes off and makes some A minus, which is the other part of the buffer as well. And that's one of the things that happens with a buffer because you have both of those components. When you add acid, it will use up a little bit of the base, but make more of the acid part of the buffer, and vice versa. When you add base, it will react with the acid and make more of the base part of the buffer. So it's almost sort of self-regenerating, use some of it and makes a little bit more of the other. But ultimately, that is really how a buffer is able to maintain the pH where it's at, because it prevents the formation of free H plus in that solution or free OH minus, and thus the H plus concentration stays relatively constant, and also does the pH. Again, as I mentioned last time, it stays relatively constant because if you really did follow with a pH meter, like you'll probably do today, you will actually see the pH move a little bit, but you will not see really big jumps in pH because you're preventing that influx of a lot of H plus really quickly or a lot of OH minus really quickly. So because you prevent that from happening, it's able to maintain it. That's the other important part about a buffer that we talked about last time that people oftentimes misunderstand is sometimes they think a buffer always has to be a neutral solution, and it does not. Again, you can make a buffer at any pH you like. Basically what it means is wherever pH it starts at, it should be able to maintain pretty much that pH even with the addition of an acid or base. We also talked about at the very end buffer capacity, which is the idea that you can blow through your buffer. So if your buffer is not made appropriately and you add too much acid or maybe too much base, you can blow through one of the parts of the buffer. And at that point, it will no longer be able to function as a buffer because you basically blew past the part that you need, and you will start to see some really big pHs. So when you want to make a buffer, you always want to think about the concentration of the acid or base you may be adding to it, and make sure that your molarity of your actual buffer is appropriate for that. Now, we talked about this with the common ion, but in reality, it really is a buffer equation, which is the same thing. And for buffer sort of problems, we can use the Henderson-Hasselbalch equation to calculate the pH, which is pH is equal to the pKa plus the log of the base concentration over the acid, where the pKa value is equal to minus the log of the Ka. We saw an example, and again, a reminder that if you want to use the Henderson-Hasselbalch equation, you can recognize it, that it is a buffer situation. then you definitely could go right into the Henderson-Hasselbalch equation in most cases. You could also still do an ice table like we talked about, and we did it last time as well. So if you want to do the ice table, you can. A reminder that if you were going to do something like an ice table with acetic acid, say, and sodium acetate, the main thing that people always screw up on when they're trying to do an ice table in a buffer situation is the initial part of that ice table. You should have molarity here. That should be 0, but you should also have a molarity on the other side. Otherwise, again, it is not a buffer. If you choose to do that, you're just going to do the weak acid problem and get the wrong answer. So you could do it either way. They both will give you the same answer. We also talked about sort of a POH version of this equation. POH is equal to the pKb plus the log, and it is reverse acid over base in that case. And the pKb is equal to minus the log of the Kb value. Once again, as I mentioned last time, I probably would have just rolled with this one, since in most problems you're really looking for the pH, I would say, in most cases. So why not just roll with that one that's going to give you the pH at the end. With this bottom one, you still have to kind of subtract 14 from it to get to the pH if that's what you're looking for. But there is a nice relationship that we also talked about, that the pKa plus the pKb equals 14. So if by some chance maybe you only have the Kb value, you can calculate the pKb and then subtract 14 from it to get the pKa pretty quickly. And that's a good little kind of workaround as well. Any questions on buffers and stuff we were talking about? All right, so obviously, as we've been talking about, obviously in a buffer solution, we can see that the pH is pretty much maintained, again, by preventing the formation of a strong amount of H plus in that solution, or OH minus. And obviously here we see a tremendous jump or drop in the pH when we add HCl. Once again here, obviously water is not a buffer solution. So we do see that big drop in the pH. And again, that's really because in water, it's going to get an influx of that H plus from the strong acid, and that's going to cause a really tremendous change in the pH that we do not see there in that buffer solution. All right, so take a moment here for each of these. Decide, can you make a buffer out of these things? Okay, let's take a look. So hopefully you know at this point what you need for a buffer, and that is one of two combinations, either a weak acid, again, and its conjugate base, or again, the salt of its conjugate base, or you need a weak base and the salt of its conjugate acid. You should hopefully also know that the only real difference between these two things is the Bronsted-Lowry difference of 1H plus for those guys to be partners. So that's really what you want to look at where you're trying to analyze these guys here. So take a look at A. We got a little KF and we got a little HF. So I see this guy and I remember my list of like 6 strong acids, and I know he's not on it. So that's going to be a weak acid. And this does look like a salt of its conjugate base. And those, again, are two things that I need for a buffer. In terms of the KF, that is a salt that's going to break apart into K plus and F minus. And it really is these two guys that is the buffer here. The potassium is just a spectator ion hanging out there, and you can clearly see the difference between HF and F minus is the 1H H plus difference between them, and that is really your buffer. By the way, obviously this would be the acid part of my buffer, and this would be the base part of my buffer, right? So I would say yes to A. Any questions on that one there? B, we got KBr and we got HBr. And again, same deal with the kind of KBr here. It is a salt that's going to break apart into K plus and Br minus. So our relationship is really between these two guys right here. And that difference is a H plus difference, which means they are related to each other. But when I look at this guy, that is what type of acid? That is a strong acid. That's one of those ones on the list. And because it's a strong acid, this guy is not going to stay together in that solution, and you will not have an acid component of that solution. You'll just have the Br minus floating around in there pretty much. And this cannot be a buffer because, again, you cannot have a buffer that has anything made up of a strong acid or strong base. So no good on that one, yeah. Lastly here, we got a little sodium carbonate and a little bicarbonate, sodium bicarb. Now on each of these are really, the sodium is not super important here. The Na2CO3 is going to break apart into two Na pluses and a CO3 2 minus. The sodium bicarb is going to break apart into a sodium ion and a bicarbonate ion. And right there, these are the two parts of our buffer in this case. That guy there, the bicarbonate, comes from carbonic acid, which I know is definitely not one of the 6 strong acids. So it is a weak acid, so probably means that guy is going to be weak as well. That's a diprotic acid, second hydrogen coming off of that deal, and that is his conjugate base. By the way, in this situation, which one would be the acid? The HCO3 minus or the CO3 2 minus? It would be this guy as your acid because he's got a hydrogen to give, right? Which is what an acid will do. It's got to donate the hydrogen. This one here, no hydrogen to give. This would be the base part of that buffer in this particular case. So this would be a buffer. Any questions on any of those there? All right. So let's do some buffer type calculations here. So we want to calculate the pH of a buffer system that contains 1 molar acetic acid and 1 molar sodium acetate. And we're going to assume in this particular case that all the volumes stay the same, that nothing is changing. And the Ka value there for acetic acid, 1.8 times 10 to the minus 5. So why don't you work on what is the pH for part A first, and then we'll talk about it. It's a buffer, and we got 1 molar of both of those things. So let's do it here, A. So we got 1 molar of acetic acid, and it's going to be mixed with 1 molar of sodium acetate. We do have a Ka value given to us, which is 1.8 times 10 to the minus 5. All right, so in this particular case, once again, even if they did not tell you it's a buffer, which they may not, you want to make sure you kind of take a peek over here and see if these things are related to each other. And obviously here we have acetic acid, which is a weak acid. It is not one of those 6. This is a salt because it has like sodium or something like that in there, which means it is going to break apart into basically the ions in solution. It is not going to set up an equilibrium, and it's going to break apart into sodium and acetate. So again, it is the acetate part and the acetic acid part that, if you look at, again, are 1H plus difference from each other. And those are your functioning parts of this particular buffer, with obviously the acetic acid being the acid part of the buffer. And here our acetate would be the base part of the buffer. So once you recognize this, it is a buffer problem. You can go directly into the Henderson-Hasselbalch equation. If you wanted to do an ice table, you could also do that like we talked about before. So just to show you, if you chose to do the ice table, as I mentioned a second ago, it is only the weak acid that's going to set up that equilibrium in solution. And your ice table would look something like this. You would start with your 1 molar there. This would be 0. And remember that it is really key to also have the molarity on the right-hand side. Otherwise, you are not doing a buffer problem in this case. You are doing a weak acid problem. Minus X, plus X, plus X. And at equilibrium here, 1 minus X, X, and 1 plus X. This obviously would go into our Ka expression. You would solve for X. X would equal the H plus concentration, which would then lead you basically to the pH, just like a normal sort of ice table that we've done before. You can sort of leapfrog all of that by, again, recognizing that this is your buffer here. So You could go right into the Anderson-Hasselbalch equation here, pKa plus the log of the base over the acid, calculating our pKa, which is minus the log of the Ka value, minus log of 1.8 times 10 to the minus 5, going to give you a 4.74. Putting that into our Henderson-Hasselbalch equation, pH equals 4.74 plus the log. The good news is it's the same concentration, so you can't mess it up. But once again, it is the base on top, 1 divided by 1. That is the log of 1, which equals 0. And that means that your pH for this solution would be 4.74 in this case. Yeah. Any questions? Obviously, that should be the same pH you would get if you went through the ice table sort of route in that case. Any questions on that there? Mm-hmm. So obviously, you don't need to do both. You could just choose whichever one you want to do. Again, if you could recognize it as a buffer, I would roll with the Henderson-Hasselbalch. Probably a little less room, hopefully, for error than maybe an ice table. Because again, as I mentioned last time, I can't tell you how many people's papers I've seen that leave this as a 0 when they try to do this type of problem. And again, they will get it wrong. Yes, I guess. Any questions on part A? All right, so part A, not too bad. Let's talk about part B, which is a very common thing that happens with buffers and something that we need to think about sort of what is going on in this situation. So if we look at part B of this problem, which is we're basically taking the same buffer solution we just calculated the pH for, and now what we want to know is what will be the pH if we add 0.1 molar HCl to this solution. Now, in this particular example, and it's not the case in most problems that you do, but in this particular example, just to keep all the numbers not too bad, we're going to assume that everybody's volume is 1 liter. So everybody will just maintain sort of a 1 liter. That, again, is not always the case. Now, there is a situation that occurs when we do something like this. So when I have a solution sitting there and I add more solution to it, does the molarity stay the same? So when you mix volume into volume and volume, does the molarity stay the same? It does not, right? Because molarity is moles of solute over liters of solution, which means when you add more volume to another volume, you're increasing the liters of solution, and that means that the molarity is actually changing. The one thing that does not change is actually the top part, which is the moles. So whenever you have a situation which occurs very commonly with buffers and definitely common with titrations, when you are adding volume to other volume, you have a situation where the molarity is constantly changing. And what that means in terms of your ice table is you need to do the first ice table in moles. And because that's going to be constant at that point. Once you do the first ice table in moles, then you should convert it back to molarity using the total volume of whatever you added. Very similar to doing like an M1 V1 equals M2 V2 type of calculation, right? We kind of divide by the total volume of everybody together at the end. And that's a similar sort of situation here. So that's what's going to happen here. So let's take a look at how we would approach part B, which is, again, we're using the exact same buffer there. We got our 1 molar acetic acid. We have our 1 molar sodium acetate. And it's still the same Ka value of 1.8 times 10 to the minus 5. But here we're going to add 0.1 molar HCl, I believe. If I'm not mistaken, 0.1 molar, yep. Now, once again, we are going to keep all the volumes in this particular example at 1 liter. That is, again, not always the case. So what's going to happen is between these two things, because this is a buffer, as we just talked about, and this is our acid part of our buffer, and this is the base part of our buffer, basically what's going to happen in this situation is that buffer is going to set up an equilibrium there in that beaker. So again, in your beaker of your buffer here, you have that weak acid basically setting up that equilibrium with a little additional acetate kind of dumped in there to begin with. So now when we add our HCl to this, which is basically a source of H plus and Cl minus, when I add the HCl, it is going to react with which part of my buffer? Will it react with the acid part of my buffer or the base part of my buffer? Since HCl is an acid, it should react with the base part of the buffer. So when you add that HCl in there, it's going to go find the base part of the buffer right there, and they are going to react. So that is actually the equation we need here for this ice table, which is going to be our HCl being added. It will react with the base part of our buffer. And this is going to do just a double displacement reaction happening. They're going to switch partners. And we are going to make our acetic acid and our sodium chloride in this case. Yeah. So that is the reaction that we're going to get. Since we are definitely adding volume in this case, we are going to do this ice table not in molarity, but in moles. So initially here, since I have 1 liter of HCl and it has a molarity of 0.1 moles per liter, that's going to give me 0.1 moles of HCl. So 0.1 moles in this case. Again, we do have to do this table in moles because we're adding volume. Molarity is changing at this point. In terms of my sodium acetate, I have 1 liter of that. Also at 1 mole per liter gives me 1 mole of sodium acetate. Acetic acid. Do I have some acetic acid? I hopefully do. Otherwise, again, this is not a buffer. Commonly put 0 by a lot of people just so they could get an X on their papers, but this is not where you want to put a 0. You also need the moles of acetic acid, which would be 1 mole as well, because it's the exact same calculation as that one right there. We have 1 liter of it, and it's 1 molar will give us 1 mole of it. All right, at this point, I am going to do my change. Now, different than a normalized ice table that we have done up until this point, our change has been the lovely letter X, right? We do some minus X's, we do some plus X's. One of the main differences that typically happen when you do an ice table in moles is you actually know what the change is going to be, and you do not use a letter. So if this is truly a good buffer, what should happen to my HCl? Should it stay there or go away? It should basically go away, right? And in this case, the change is going to be my HCl. It is, by the way, logically speaking, the smaller number, right? So if you take a bigger number, start subtracting, you're going to get a negative number. That's not so good. So this is going to be a minus 0.1 moles based off of HCl being like the limiting reagent. This is going to be minus 0.1 moles. This is equivalent to doing minus X, and plus X on the other side. This is going to be a plus, also missed by a lot of people. They want a minus on the other side as well. When I reach equilibrium here, I will have none of that left over. We will have a wonderful 1 minus 0.1, and that's going to be a 0.9 moles. And we're going to have a 1.1 moles happening on the other side as we add that together. First off, any questions on the table here? So a little slightly different. Typically speaking, if you're rolling with moles in your ice table, probably going to know what the change is, and you'll roll with a number. By the way, why, oh why, am I ignoring sodium chloride? It is a salt. What kind of salt is it? It's neutral. So why put numbers there that you're going to use wrongly, right? So it's not going to affect the pH. Might also not put any numbers there. If you want to, you can, but you do have to recognize at the end it's not going to do anything, right? So you don't want to get confused. So if you can sort of just kind of know, you can just kind of leave that out of the way. As it's a neutral solid, it's not going to affect the pH. Yeah. We're not using molarity because we're adding volume to volume. So when you do that, molarity changes because it's moles per liter solution. What doesn't change is the number of moles. So to be truthfully honest with you, when you look at a buffer, the only thing that is really there to react are the moles of the acetic acid in this example and the moles of sodium acetate. Those are really as much buffering as you can handle in that particular situation here is whatever moles you start with, and that's really what's reacting. Everything else is just floating around. It's really those things that are sort of reacting. Now, a absolutely positively thing that you should just roll with on autopilot at this point is when you get done with this first ice table that you have done in moles, you should convert everybody back to molarity at this point. Now, the reason you should do that is it's going to set you up for success in later calculations, because I would say 9 times out of 10, you are going to need molarity to roll on with the rest of the calculation. And if you leave it in moles, you're going to forget somewhere down the road to convert it back to molarity, and you're going to end up with the wrong answer. So it should just be automatic to convert it. To convert this back, we're going to divide by the total volume, which in this case is 1 liter. You would divide by the total volume. Now, if we didn't keep the volume constant in this case and we had 100 milliliters of buffer and we added 20 milliliters of HCl, our total volume at the end, right, it's 120 milliliters, right? And you would divide by 0.12 liters to convert it back. So in most problems, you do have to take the volume into account. So it's whatever the volume of your buffer is and how much you're adding would get you your total volume there at the end. That's going to get us 0.9 molar. We'll divide that by 1 liter, going to get us 1.1 molar at this point. We're talking any questions on that there. Now, sometimes people get to the end of this and they go, I'm not really sure what I should do at this point. So your ice table does help you sort of hopefully understand what you have left. And if you look at your ice table, you should see that you have this guy left, which is acetic acid, and you have sodium acetate left. We kind of already eliminated not worrying about that guy, right? And you should hopefully still recognize that these two guys is still a buffer. So you still have your buffer left over at this point. Yes, sir. Yeah, so just in this particular case, this problem, we're keeping everything at 1 liter. Just keep it. Normally, you'd be correct. If we added a liter and a liter, you would add them together. But just for this one, we're just going to keep everybody's volume just constant. Yeah, but absolutely correct. In normal problems, you would add all that together to get it. Yeah. So this is still a buffer, which actually now opens up for you 2 options. You can again do an ice table if that's the route that you want to take. You would probably lay up the acetic acid. You would actually lay up this right here as your ice table equation, the acetic acid. But because it's a buffer, you don't need to do that. You can now just go right into, again, the Henderson-Hasselbalch equation. So I'm going to go into pH is equal to pKa plus the log of the base over the acid. My pKa is still the same from part A, which is 4.74, plus the log. We want to make sure we get this right. So remember, the one with more hydrogens is my acid, so that's my base, 0.9, 1.1 in this case. And if we go 0.9 divided by 1.1 and we do a little log action on it, and you add it to 4.74, going to yield us a 4.65 in this case as our pH. Now, the buffer by itself in part A had a pH of 4.74, right? We just added some acid to it, and we see the pH went down a little bit, but it did not drop a lot. and it did move in the correct direction. So if you did this calculation, you ended up in part B with a pH like a 5, you're moving in the wrong direction because you're adding acid. It should not be going up. Yeah, it should be going down. So these are the things you should think about in terms of doing this calculation. Now, why I said that you should convert it back to molarity at the end of the first ice table is you usually will need it to for the rest of the calculations. The one exception is if you wanted to, and you are using Henderson-Hasselbalch equation, you can leave the base and the acid in moles, and it'll come out exactly the same because here the volume will just get divided out. But if you're not using Henderson-Hasselbalch, you should have definitely converted it into moles, to molarity. And I would recommend just even if you're using Henderson-Hasselbalch, convert it to molarity. It's just a really good habit. It's a very good habit to have, especially when you get into titrations where you're doing some other calculations. Just convert it back to molarity. But truth be told, you can go into Henderson-Hasselbalch with moles of each of those things, and it will come out the same. So you will get the same answer on that. Any questions on that there? Now, we talked about earlier that there is a buffer capacity and a limit to how well a buffer could work. So why don't we use this example here to illustrate what would happen if, maybe you screwed up on something. So we're going to do this exact same thing. We're going to take the HCl. We're going to add it to our sodium acetate here. And again, we're going to get our acetic acid and our sodium chloride here. And again, we're going to assume that we had our 1 molar of this guy and our 1 mole of this guy. Sorry, not molar, but 1 mole of this sodium acetate and the 1 mole of acetic acid. So again, instead of going to the shelf and grabbing the HCl that has the 0.1 molar label, you decided that the HCl with the 18 molar label looked just as good and probably pretty similar. And you decide to grab the 18 molar HCl. And if you took 1 liter of 18 molar HCl, don't ever do that in our lab. But if you take 1 liter of 18 molar HCl, that will give you about 18 moles of HCl you're going to add to this poor, sad buffer at this point, probably. Now what's going to happen when we try to do our change? What is now the limiting reagent? Is it still the HCl? It is not. You have nowhere near enough moles of sodium acetate to help out with that 18 moles of that acid you just did in there. So it's actually going to be this guy that's going to be your limiting reagent in this case because you added way too strong of an acid for your poor little buffer. And the change here is actually going to be -1, -1 mole, and +1 mole, which means at equilibrium, you have about 17 moles of this guy, you'll have none of this guy, and you'll have about 2 moles of this guy. What you have left at this point is acetic acid and HCl. Is that still a buffer at this point? It is not. You actually have 2 acids. You got a weak acid, and you have a heck of a lot of a strong acid floated in there. Your pH is going to go way down. Yes, it's going to drop out of the pH range there pretty much. And that's what I was talking about before. A buffer is only as good as how many moles of your acid part and your base parts that you have in there as to how it could help out when you're adding additional acid or base to it. So those are things that you want to think about. And perhaps maybe you are adding, for example, a lot of acid or something. You may actually want to make your buffer with a little bit more base part, right, to start with, right? So that as it gets used, you're not using it all up. So these are things that you kind of want to think about. Any questions on that there? Okay. All right. Well, why don't you give this one a go? Calculate the pH of a 0.3 molar ammonia and 0.36 molar ammonium chloride buffer system. What is the pH after addition of 20 mils of 0.05 molar sodium hydroxide to 80 mils of this buffer? So we're looking for the pH of the buffer by itself, and then we're looking for the pH of the buffer after we add the sodium hydroxide to it. We are not keeping the volumes constant here, so you do have to take them obviously into account in this case. Let me give you we'll do a Ka value, I guess. Let's see. I'll do the Ka for, actually no, let's do Kb. Let's have fun. Kb value for NH3 is 1.8 times 10 to the minus 5. I know you're thinking, like, I just saw that number, but it's also this guy. All right, why don't you give it a go, see what you come up with here. So again, looking for two answers kind of before addition and after. Okay, let's take a look, see how you're doing. So obviously, it tells you it's a buffer, but once again, lots of problems, they will not tell you it's a buffer. So we do have 0.3 molar ammonia, and we do have 0.36 molar ammonium chloride. So once again, with say the Kb value given to you, you should recognize that this is a weak base, and this would be his conjugate acid, really the salt of his conjugate acid. That is a salt, which means it's really going to break apart into NH4 plus and Cl minus. And right there, that and this is your buffer. That is your active sort of parts of your buffer, with obviously the NH3 being your base in this case. And here we see we have the guy with one more hydrogen being the acid part of the buffer, right? So that's your acid part of the buffer. That's obviously your base part of the buffer in this case. Now, again, that's important to be able to recognize that, because like I said, a lot of problems, they will not just straight up go, hey, it's a buffer. They'll just say you made a solution of these two things, what's the pH of it? And you need to be able to recognize that these things are buffers. Now that it is a buffer, we're looking for what is the buffer before and after we do some addition. Now, before we do the addition, we are not adding any volume. It's just the buffer itself, which means we don't have to worry about doing things in moles or anything like that, because we haven't added any volume to it. We also have, again, two choices as to how you could get the pH of the buffer. You can either do an ice table, or you could do the Henderson-Hasselbalch equation. You actually have several options as to how you could get to this answer. If you chose the ice table, you could do a Kb weak base ice table. You could also convert the Kb into a Ka and do a weak acid ice table with NH4 plus. You can also do the Henderson-Hasselbalch equation, and you could even, because this is kind of like a basic sort of buffer, most likely going to end up being, you could also use the POH version of that Henderson-Hasselbalch that we talked about. A lot of options. Choose the one you're comfortable with. I would roll still with, no matter if it's acidic, basic, neutral, you could always use just the run-of-the-mill there Henderson-Hasselbalch equation, as long as you identify it as a buffer. You need a pKa value here, right? So you do have the Kb. And like I said, you also have some options. You could calculate that to the pKb and subtract 14 to get the pKa. You could also just use good old-fashioned Kw action there and do 1 times 10 to the minus 14 divided by our Kb value, just like we did with Kw. And that will get you a 5.6 times 10 to the minus 10. And you could turn that into your pKa value of minus the log 5.6 times 10 to the minus 10. And that's going to give you a pKa of 9.25 in this case. If you chose the pKb and subtracting 14 root, you will probably end up with 9.26 as your pKa value, which is okay as well. But again, just because of rounding, you'll get a slightly different sort of pKa value. Any questions on that part of it there? Now that, I have everything I need just to calculate the pH of my buffer to start with. 9.25 plus the log. Once again, we want to go with the base up on top, 0.3, and divide it by 0.36 in this case. And that's going to get us here 0.3 divided by 0.36 log and a plus 9.25. Going to open us up here with a 9.17 as our opening pH of this buffer, which again is a basic buffer, no big deal. Henderson-Osbach can handle it. Any questions on that there? Now, again, just to illustrate, if you chose ice table instead, like I said before, you could actually just do NH3 plus some water, little NH4 plus, and OH minus. Initially here, this would be 0.3. This would be 0.36. Again, important for it to be a buffer. And this would be 0. Obviously, minus X plus X plus X. And 0.3 minus X, 0.36 plus X, and X. This would go into your KB. You would solve for X. It would be the hydroxide concentration in this case, giving you the POH and then the pH. You also could have done this and used the NH4 plus as a weak acid, dissociating into NH3 and, excuse me, you could do H plus or H3O plus if you like, whichever way you want to do it. You can put the water in as well on that side. But if you chose this, initially this would be 0.36, this would be 0.3, and this would be 0. This would be minus X plus X plus X. 0.36 minus X, 0.30 plus X, and X. This would go into your Ka. When you solve for X, it would equal your H plus concentration. So again, on this particular one, you do have a variety of sort of ways that you could kind of do it. Any questions on that first part there? And obviously here you can put the water in and get the H3O plus on the other side as well if you chose to do so. All right, let's take a look at the second part here, which is we're going to take 80 milliliters of this buffer. We're going to take 80 milliliters of this buffer that is made up of 0.3 molar NH3 and 0.36 molar NH4Cl. And to that, we're going to add 20 milliliters of 0.05 molar sodium hydroxide, right? Make sure there. 0.050. Yep. All right. So this is obviously a situation where we are adding solution to our buffer, right? So we're adding volume to volume. So we do need to do an ice table here. This ice table does need to be done in moles to see how our buffer is going to change as a result of adding this sodium hydroxide to it. So we need some moles of everybody. So divide 20 by 1,000 or move the decimal. Convert it to liters. 0.05 moles per liter will give us 0.02 times 0.05, 0.001 moles of sodium hydroxide. Now, just so we're clear, if you have a buffer sitting here, both of these things are in your buffer to start with. You got both of those guys in there, and the total volume here is going to be 80 milliliters for both of them. So 0.08 liters times our ammonia, 0.3 moles per liter. Gonna get us here 0.08 times 0.3, 0.024 moles of ammonia. And again, the 80 milliliters goes for our other buffer components because they are sitting in the same beaker, 0.36 moles per liter, NH4 plus in this case. 0.08 times 0.36, 0.0288 moles of NH4Cl. All right, now that we got the moles of everybody, we could do our ice table here. And we're going to add the sodium hydroxide, which obviously is a base. And when it reacts with it, it will react with the acid part of our buffer. And we're going to get some ammonium chloride here. If you want to keep the chloride in there, it's just hanging out as a spectator ion. In this particular case, this is our acid. It's going to send it over the H+. You are going to form water. You will form ammonia. And for good measure, you'll pop a little sodium chloride in there as well. So you get a few things that will also be formed in this case. If you want to simplify, you could take this chloride out. But we're not too concerned about this guy since it is sodium chloride in this case. And again, it is this guy sending the H+ over to there. So initially here for our hydroxide, we have 0.001 moles. For our ammonium chloride, we have 0.0288 moles. And for our ammonia, we have 0.024 moles. I'm not going to worry about water, right? Because it's not going to do anything for the pH. And we've already kind of eliminated this guy as well as being neutral. So once again, maybe don't put numbers where you might use them incorrectly. In this case, we should know the change. We look there to the left and we do see that the sodium hydroxide is the limiting reagent. There's less moles. And if you remember nothing else from this conversation, you should always take the smallest number. I know that seems logical to you, but there will come a point where you will want to take the bigger number. Don't do it. Yes, always take the smaller number, even if your head tells you to take the bigger number. Yeah. I've seen it on many exams. All right, here we go. So we're going to plus that all the way across there on the other side and subtract. That's going to zero out our sodium hydroxide, which hopefully means our buffer is working. We're going to go 0.0288 minus 0.001. That's going to get us 0.0278 moles. And we're going to actually be adding on this side, not subtracting, which again is a common error that people make. We're going to end up with 0.025 moles on this side. At this point, like I said earlier, it should just be kind of automatic. We want to convert these moles back into molarity. So we're looking at our total volume at this point. So obviously we had 80 milliliters of our buffer, and to that we added 20 milliliters of base. That's going to give us a total volume here of 100 milliliters, which means we're going to divide each of these by 0.1 liters to convert these guys back into molarity. So if we do that there, it's going to move a little decimal point over. 0.25 molar. And obviously here, 0.278 molar. Any questions so far on the ice table or where any numbers came from? All right, at this point, if you still maybe don't know what's going on in terms of what you got left at this point, the ice table can be really helpful for you. You should hopefully be able to see you have NH3 left over, and we got some NH4 plus left over. These guys are still a buffer, right? So we still have a buffer left over at this point. And that means, again, probably the simplest solution to get the pH at this point is the Henderson-Hasselbalch equation. Once again, you could also still do your sort of ice tables if you wanted to. So we're going to go pH is equal to pKa plus the log of the base over the acid. It's the same weak base or weak acid, so it's still 9.25 as our pKa as in the first part, plus the log. Once again, we do want to make sure we get the base, which is our ammonia, up on top, 0.25 divided by our acid, 0.278. That's going to get us here a pH after we add the base of 9.20. First off, any questions on that there? Our pH of our buffer before we added anything was 9.17. I just added some base to it and it went up to 9.20. Again, our buffer worked pretty good. It didn't have a big change in pH in this case. Bless you. It also went in the correct direction. I added sodium hydroxide, which is a base, which means my pH should go up a little bit. Once again, if you did this calculation, you ended up with a pH less than 9.17. You're going in the wrong direction based on the fact that you're adding base. Your pH should go up a little bit. But again, our buffer worked pretty well here. Not a big jump in pH in this example. Any questions on that there? All right, we're going to lay that